You think the speed of light is merely a number? 299,792,458 meters per second. Fast. Extremely fast. The fastest phenomenon we know. Okay, but why is it the limit? Why can't anything move faster? What actually stops it? Most people have never seriously asked this. They just accept it. Einstein said so. The speed of light is the universal speed limit. That's just the way things are. But that isn't an explanation. That's just repeating phrases. When you genuinely ask why nothing can exceed the speed of light, when you investigate what is truly preventing it, you uncover something so bizarre, so radically different from everyday intuition that it reshapes everything you believe about space and time. The speed of light isn't simply a velocity. It isn't just the fastest thing. It is the structure of the universe itself. It is embedded in the fabric of space and time in a way that makes going faster literally meaningless. Let me show you what that means. Let's begin with something simple, something familiar to everyone. Objects fall. Drop something, it falls downward. 16 feet in the first second, to be precise. That's what Galileo measured. Drop a ball, drop a rock, drop anything, and in 1 second, it falls 16 feet. Now consider the moon. The moon is moving around the Earth. It isn't falling straight down. It stays up there, orbiting in a circle. But hold on, is it falling? Think about it. If the moon were just hanging in space, not moving sideways, what would happen? It would fall toward Earth. Gravity would pull it inward. But the moon is moving. It's moving sideways, tangent to its orbit. And because it's moving sideways, while gravity pulls it downward, it keeps missing the Earth. It falls toward Earth, but never quite hits it. That's what an orbit is. Continuous falling while moving sideways fast enough to keep missing. Now here's where Newton had his brilliant insight. The moon is 240,000 miles from Earth's center. We're standing on the surface 4,000 miles from the center. So the moon is 60 times farther away than we are. Newton asked, what if gravity weakens with distance? What if it follows an inverse square law? That means if you go twice as far away, gravity becomes 4 times weaker, 3 times farther, 9 times weaker, the square of the distance. If that's true, then at the moon's distance 60 times farther, gravity should be 60 squared times weaker. That's 3,600 times weaker. Now on Earth, objects fall 16 feet in 1 second. If gravity at the moon is 3,600 times weaker, then the moon should fall toward Earth by 16 feet divided by 3,600. Do the calculation. 16 feet divided by 3,600 is about 1/12 of an inch per second squared. Let me restate that. In 1 second, something at the moon's distance should fall toward Earth by 1/12 of an inch times 3,600 because time appears squared in the equation. 1/12 of an inch multiplied by 3,600 equals 16 feet. Exactly what we measure on Earth. Newton calculated how far the moon should fall toward Earth in 1 second if gravity followed an inverse square law, and it matched perfectly. The moon is falling at precisely the rate Newton's law predicts. This was enormous. This wasn't just speculation. It was a prediction. Newton took one completely independent fact, how fast objects fall on Earth, and linked it to another completely independent fact, the moon's orbital period and its distance from Earth. Two things that seemed totally unrelated were suddenly united by one law, the law of gravitation. There was no turning back. Newton went further. He calculated the shape planetary orbits should have if gravity follows an inverse square law, and he found they must be ellipses. And sure enough, planets do move in ellipses. Kepler had already measured that, but he didn't know why. Newton explained it. He got 3 for 2, as it were. Then more pieces fell into place. The tides. Why do tides exist? Because the moon pulls on the Earth. But wait, if the moon simply pulled Earth toward it, there should only be one high tide per day, right? A bulge of water on the side facing the moon. But instead there are 2 tides per day, roughly every 12 hours. Why? Some thought Earth was pulled away from the water. Others thought the water was pulled toward the moon. Both were partially right, but neither was complete. Newton realized what was actually happening. The moon's gravitational force on Earth and on the water is the same at the same distance. But the water on the near side is closer to the moon than Earth's center, so it's pulled more strongly. And the water on the far side is farther from the moon than Earth's center, so it's pulled less. That creates 2 bulges, one where water is pulled toward the moon, and one where water is left behind because Earth is pulled more than that water. 2 tides per day. In fact, Earth performs the same trick as the moon. It moves in a circle. The center of that circle lies somewhere inside Earth. Earth and moon both orbit their shared center of mass. If you like, the water is flung outward by centrifugal force more than Earth itself. and this water is attracted more strongly than the Earth's average mass. Either way, the tides were explained, including why there are two each day. Many other things became clear. Why Earth is round, because everything is pulled inward. Why it isn't perfectly round, because it spins. The outer parts are flung outward slightly, balancing gravity. Why the sun and moon are round, and so on. As science advanced and measurements became more precise, tests of Newton's law grew stricter. The first careful tests involved Jupiter's moons. By observing their motion over long periods, scientists could check whether everything followed Newton's laws. It turned out that it didn't. Jupiter's moons appeared sometimes 8 minutes ahead of schedule, and sometimes 8 minutes behind, where schedule meant the predictions from Newton's equations. 8 minutes. That's a massive discrepancy. Something was wrong. But then it was noticed that the moons were ahead of schedule when Jupiter was closer to Earth and behind schedule when Jupiter was farther away. Strange indeed. Romer, confident in the law of gravitation, reached a fascinating conclusion. Light takes time to travel from Jupiter's moons to Earth. What we observe is not how the moons are now, but how they were some time ago, the time light needed to reach us. When Jupiter is closer, the light takes less time. When it's farther, it takes longer. By correcting for this timing difference, how early or late the moons appeared, he could calculate the speed of light. This was the first proof that light does not travel instantaneously. Think about what just happened. We discovered the speed of light without measuring light directly, but by trusting the law of gravitation. When observations didn't fit, instead of discarding Newton's law, Romer asked, what if light takes time to travel? And he was correct. I highlight this because it shows something profound. When a law is correct, it can be used to discover another. Trusting one law allows discrepancies to reveal new phenomena. Without knowing gravity's law, it would have taken far longer to find light speed because we wouldn't know what to expect from Jupiter's moons. This process became an avalanche of discovery. Each new result provided tools for more discoveries. That moment marked the beginning of an avalanche that has continued for 400 years uninterrupted, and we're still racing downhill today. But here's the key point. Once you know the speed of light, once you measure it, you notice something deeply strange. Light always travels at the same speed. Always. No matter who measures it, no matter how fast they're moving. Let's make this concrete. You're standing still. You shine a flashlight. You measure the speed of the light. 299,792,458 meters per second. Fine. Now you board a train, a fast one, moving at half the speed of light. You shine the flashlight forward in the train's direction of motion. Common sense says the light should now move at the speed of light plus the train's speed. Like throwing a ball forward from a moving train, it goes faster than if you threw it while standing still. But that's not what happens. You measure the light, and it's still moving at 299,792,458 meters per second. Exactly the same. You think I must have made a mistake. So you speed up the train to 90% of light speed. You shine the flashlight again. Still 299,792,458 meters per second. You get annoyed. You push the train to 99.999% of light speed. You shine the flashlight. Same result. The speed of light doesn't add. It doesn't combine with your speed. It stays constant no matter how fast you're moving. This should completely break your intuition. This is not how motion works in everyday life. Speeds normally add. If you're on a train moving 50 miles per hour and you walk forward at 3 miles per hour, you move at 53 miles per hour relative to the ground. But light doesn't behave this way. Light always moves at the same speed relative to you, regardless of your motion. Why? Einstein figured it out. And it was so strange, so against common sense, that even now, more than a century later, people still struggle to accept it. Space and time are not fixed. They are flexible. They stretch and bend to preserve the speed of light. When you move faster, time slows down for you. Your clock literally ticks more slowly, and distances contract, the space ahead of you compresses. These effects are real, they aren't optical illusions. They aren't measurement errors. Time truly slows, space truly contracts, and the amount of change is exactly what's needed to make the speed of light identical for everyone. Let me repeat that. The universe adjusts space and time, bending them, stretching them, compressing them, to ensure that light always travels at the same speed for all observers. The speed of light isn't just a speed, it's a structural constant of reality. Space and time are arranged so that this speed is invariant. Now it gets even stranger. If you try to accelerate anything at all to the speed of light, something bizarre occurs. The closer you get, the harder it becomes to go faster. It's not that you run out of fuel. It's not that engines aren't powerful enough. It's that the object itself increasingly resists acceleration. This is called relativistic mass increase. As speed increases, inertia increases. Pushing it faster becomes harder and harder. As you approach the speed of light, inertia approaches infinity. To actually reach light speed would require infinite energy, which is impossible. So nothing with mass can ever reach the speed of light. Not because of arbitrary rules or engineering limits, but because space-time structure forbids it. Light can move at that speed because photons have no mass. Zero. Massless particles can travel at the speed of light. In fact, they must. They have no alternative. But anything with mass can only approach it, get extremely close, 99.999%, but never arrive. The universe refuses. You might ask why. Why is the universe built this way? Why does a speed limit exist at all? And here's the frustrating answer. There is no deeper why. The speed of light isn't a limit imposed on the universe. It's a consequence of how the universe is constructed. Space and time aren't separate. They're fused into space-time. And space-time has a geometry, a structure. That structure contains a built-in conversion factor between space and time. That factor is the speed of light. It's not that light is special. It's that space-time has a maximum rate at which cause and effect can propagate. Light travels at that rate because it has no mass. But the rate itself belongs to space-time, not light. Even if light didn't exist, the limit would remain. It's a property of reality itself. Here's another way to think about it. In daily life, you treat space and time as separate. You move through space, time flows. They seem independent, but they aren't. You're always moving through space-time at a constant rate. Always. That motion is divided between space and time. If you're standing still, all of your motion is through time. You're moving into the future at the maximum rate, 1 second per second. But once you start moving through space, some of that motion is diverted away from time. You're now moving through both space and time, meaning your motion through time slows. The faster you move through space, the slower you move through time. There's a limit. If you could move through space at the speed of light, you'd have no motion left for time. Time would stop for you. That's why light doesn't experience time. From a photon's perspective, emission and absorption happen in the same instant. No time passes. The universe is frozen. You can't exceed the speed of light because you can't have less than zero motion through time. That's the boundary. That's the wall. And here's the beautiful part. This isn't just theory. We've tested it again and again. Particles and accelerators reach 99.999% of light speed. And exactly as predicted, the closer they get, the harder acceleration becomes. GPS satellites must correct for time dilation. They move fast and sit in weaker gravity, so time passes differently for them than for us on Earth. Without correction, GPS would drift by miles each day. Muons created high in the atmosphere by cosmic rays should decay before reaching the ground. Their lifetimes are too short, but they move near light speed, so time slows for them. From their frame, they live long enough to reach the surface. From ours, they live longer because they're moving fast. Either way, more muons arrive than classical physics allows, exactly as relativity predicts. This isn't speculation, it's measured. The speed of light as a limit is among the most thoroughly tested facts in physics. So let's tie it together. Why is the speed of light the limit? Because space-time has a structure with a maximum rate of cause and effect. That rate is the speed of light. Not because light is special, but because space-time has a built-in conversion between space and time. You can't exceed it because doing so would require moving backward in time, which is meaningless. You can't have negative time. You can't reverse cause and effect. The speed of light is the speed at which now moves through the universe. It's the speed of information, the speed of forces, the maximum rate of change. And this entire avalanche of discovery began with Newton watching the moon, then Romer watching Jupiter's moons, then Einstein realizing light speed is constant and deriving relativity, then thousands of experiments confirming it. Each discovery built on the last. Each insight unlocked new doors. That's how science works. That's the avalanche that's been rolling for 4 centuries. And we're still racing forward today. The speed of light isn't just a number. It's the key. It unlocks how space and time function. It reveals a universe stranger and more beautiful than we ever imagined. And the fact that we can understand it, measure it, test it, and predict with it, that's the beauty of physics. Not comfort, not simplicity. Truth.